Why do people go bald?
Why are baboons' bums red?
What's a light year? Why do leaves go brown in the autumn? Why do monkeys like bananas? Why do some things glow in the dark? Why do animals not understand you? Why do my receipts fade after a year?
Don't know the answer? Ask the Naked Scientists.
Hello and welcome to this week's Ask the Naked Scientists with me, Sue Marchant, and Chris Smith. Now, Gus in Little Massingham has sent a little email in to say an American professor has recently stated that except for rare physical abnormalities, at the present time there is no evidence of a direct causative link between a single gene and complex psychosocial behaviour such as sexual preference. Whilst genetics play a role in a person's predispositions, this is a far cry from predetermining that a person will engage in certain behaviours such as homosexuality. And he goes on to say, what do you think? Do gays really develop that way, or are they born to their behavioural tendencies? It would be interesting to know which you think it is.
I think the best way of thinking about this is to view behaviour as a spectrum. So rather than having a behaviour or not having a behaviour, we view the way that we behave socially as a bit like a bell-shaped curve. This is where if you drew around the outline of a bell, you'd get a curve which goes up and peaks in the middle and then comes down, so it's sort of flared at either side. And what we know about the way behaviour is that within that fairly broad region there's a whole range of different behaviours that could be described as normal. So there are some people that behave very differently at one end of the bell to people at the other end, but they're still both normal. And therefore, is someone totally homosexual, or are they totally not homosexual? Well, some people probably are, but there might be some people in the middle somewhere who actually, I suppose you use a horrible analogy, but bat for both sides. And is that therefore abnormal? Probably not. It's just part of the spectrum of what is human behaviour. And given that you've got this bell-shaped curve, you can't get that kind of distribution of behaviours from a single gene. And I find it very unlikely, just from a genetic perspective, that that a single gene would determine whether or not we were homosexual. Because such a gene, why would we have a gene like that? It's more likely that these behaviours are controlled by a whole cluster of different genes that work together to make us behave in a certain way. And let's be honest, no one has the faintest, foggiest clue what it is that makes one person be attracted to another, whether they're male or female. So trying to understand another layer of complexity, which is why someone is attracted to that person who is also the same sex or a different sex to them, is really difficult. And scientists just don't have a clue what drives that, and there's never been any consistent genetic studies showing that the same sets of genes are associated with it. So at the moment I can't give you an answer as to what genes are associated with people behaving in certain ways, except in rare circumstances where there are certain genes which have been linked to certain types of behaviours, but they're nothing to do with sexual behaviours on the whole. They're usually associated with violent behaviour or unpredictable behaviour, for example. There are certain forms of certain genes that affect a person's behaviour and might make them more prone to be violent or to have outbursts, for example. But there are no single genes that are linked to being homosexual or being non-homosexual.
Thank you, Chris. Tony from Westcliff. Hello, Tony.
Hello, Sue. We always talk about genetic engineering and so on. I just wondered whether perhaps in our lifetime, or your lifetime certainly, they'll be able to make, say, monkeys talk by, giving them a voice box.
Don't know. I don't know whether it would be allowed either. The way in which we think this works is that pretty much every animal on Earth can understand things and learn to understand things. There are dogs around, for instance, in Germany that can understand thousands of words. There's a collie dog called Rico, which has a vocabulary of several thousand words. Researchers have been able to show that it has the learning ability of a 3 or 4 year old human. Certainly when it comes to language. So dogs can definitely understand words, and so can monkeys, so can dolphins even. They can learn to process the sounds and recognise certain word patterns. Whether or not they have the ability to translate words back into the kind of very accurate movements you would need to make speech sounds, I don't know. Whether they would be able to do that meaningfully, I don't know, because there's more to speech than just making noises, because you have to, in your brain, select what sounds you want to make, in other words, what words you're going to make, then you have to execute those movements, and then you make the sound. Now, the problem is that if you don't understand what it is that you want to say, it's no good knowing how to make all the movements without knowing what you want to say. And similarly, it's no good knowing what you want to say if you can't make all the movements. And they're two different parts of the brain. So I think there's sort of two problems tied up in that. And do we really want to make monkeys talk? I'm not sure.
Not particularly. I mean, parrots talk, but they don't really... Do you think they know what they're saying?
I think it's almost certain that they don't. They don't actually infer meaning. They're just very good at mimicking. And this is because when birds grow up, they communicate with sound and they copy what the adult birds do in order to learn their song. And it's interesting because researchers have done studies on birds as they age, and they've shown that they go through a sort of teenaged angst phase in the same way that humans do. So they don't paint their nests black and dress all in dark clothes, but they do certainly change their song choices in the same way that the average teenager does when they reach teenage. And so birds start off with fairly conservative tastes in adult song. They then become very adventurous in their teenage years, and then they settle down to a song which is based on what they learned as a child, but is a little bit unique to them when they're older. So I think that this is based on mimicry, though, Tony. It's not based on them understanding what they're doing and then wanting to put some kind of additional meaning into it. In terms of other animals, don't know. We know that dolphins and whales talk to each other using certain sounds, and there's a guy up in the University of St Andrews who has been recording sounds that dolphins, for instance, and certain whales make when they're hunting, and they've been able to define certain sequences of noises that they make to signal certain types of behaviour that they're about to make in order to catch prey. So this is the way in which they orchestrate and organise between them how they're going to round up a school of fish and eat them, for instance. They've also made recordings from marine mammals in different parts of the world and shown that they seem to have regional accents, a bit like humans. So in the same way as we have Welsh accents, Scottish accents, Southern English accents, estuary, you get the same thing with marine animals. We also know that birds living in cities also change their song compared with birds living in the countryside to overcome the sound of the traffic.
Bless you. Bye.
Bye. Alan has got a question, so has Leon, but the first one that we came up to on the text was about the circumference of rope. So do you know at what circumference does string become rope?
It's interesting. I hadn't even ever thought about this. So I had a little sneaky look on the internet because I wasn't sure. I haven't found a specific definition in terms of inches and centimetres, but what I can say is that there is this definition in terms of rope is the thickest stuff which you can get, and is usually made of lots of different fibres wound together. And the idea of that is that you get the individual strength of the individual fibres, and when they're wound together, they add together, and so you get a much stronger substance than if you just had one individual strand, for example, but it was very, very fat. So rope is at the top of the list. Next down on the pecking order is cord, which is thinner than a rope but fatter than a string, and at the bottom of the list is a thread. So I suppose you could consider that you could take all of those things. You could take the thinnest, a thread, and you could wind lots of threads together to make a string. You could wind strings together to make cords, and then you could wind cords together to make ropes, and then you'd have really strong cables, I suppose, if you wanted to take it to its massive extent. But when you make wires, for example, if you want to make a suspension bridge, you wouldn't just cast a strand of wire or stretch out or draw out a strand of wire and then suspend your bridge on it, because it wouldn't be very strong. And most cables or hawsers are made in exactly the way I just mentioned, where you twist wires together and you have multiple strands and they're all bearing the load, they're sharing the load, so the actual amount of tension in each one, the actual strain is therefore the same because it's stretching, but the actual stress across each of the fibres is different, it's much less, and therefore you have a much lower chance of it failing.
Right, thank you for that. Alan from Harlow asked that whilst talking about words plus understanding, how did the world become the bearer of so many different languages? Would it not be possible for all countries to speak in a common tongue?
Well, perhaps when we all lived in just one place on Earth, that would have been the case. We all came... We separated off from chimpanzees as a race about 6 million years ago, so we've got 6 million years of evolution under our belts now, and the earliest remains of humans go back about 5 million years or so, and they're humanoids, so they're not exactly like us. Then there are quite good fossils in South Africa of Australopithecines, which are a bit like us, but they had much smaller brains, they tended to be smaller, and they were still quite similar to a monkey. They had no chin, for example, when you look at their skulls. And then the Australopithecines turned into Homo erectus, and that's much more similar to us. And then from Homo erectus, we suddenly appear. And humans, we think, pop up in Africa about 150, 200,000 years ago as modern humans. And we left Africa and populated the whole of the world about 55,000 years ago. Now, that means that at one time we were all conglomerated in pretty small numbers, probably, in one place, and that's Africa. But then, very rapidly, modern humans dispersed, and they went right around the world, taking language with them. The thing is that because we didn't travel very far, people weren't very mobile, they tended to be hunter-gatherers at that time, and they therefore went where the food was and went where the weather was nice. They very rapidly got dispersed across the globe. And scientists have a pretty good idea as to how people, early man, spread around the globe now from Africa 55,000 years ago. And one clue that they've got to how this happened is that there is a bacterium that lives in quite a few people. It's called Helicobacter pylori. We now know that it is linked to stomach ulcers and stomach cancer. But it can be carried for a long period of time in people without appearing to do them any harm. They don't know they've got it, so they're not symptomatic. So therefore, it doesn't harm people to carry it that much. Therefore, it's ferried around wherever the people go. And as a result, you can look at the genetics of the bugs, the Helicobacter pylori, carried by populations from around the world. And because it's got DNA in these bacteria, you can use the rate of change of the DNA over time. We know how fast it mutates, for example. You can use the different strains of Helicobacter pylori in human populations around the world to work out how we must have migrated. And that's how scientists know the migration patterns of humans getting right round the world out of Africa to all the different countries they colonised. And this enables you to identify the time it took people to get from point A to point B. And what we know is that humans didn't mix up very much. They formed these little populations in various places around the world, and that was them. And, of course, they would have communicated with each other, but not with other populations around the world. So this separation, in the same way as separating animals can lead to new species emerging, in the case of humans, separating us led to the emergence of languages, because we learned to speak. People had the ability to communicate using speech and words, but they needed to develop their own grammar. And by having everyone so spread out, that meant that the same principles were used to drive the development of different languages, but they didn't have very much in common. And it's interesting because if you look at the languages across Europe, for example, things like Spanish and French and Italian and English, they're all very similar. They're Latin languages and they have a lot in common. And the same things happened since the Romans had Europe under their control a couple of thousand years ago. Latin has given way to modern languages which still derive a lot of their language from that Latin, but nowadays we struggle to be understood between each other. So if you leave the coast of England and go to France, then there's a bit of a language barrier. Usually not so much these days because the French speak better English than we do, but that's exactly why it is. So it's all to do with separation.
Daniel has sent a question in by email. He says, what happens to the particles in a piece of fabric when the fabric fades?
Right, OK. That's an excellent question. When you dye a piece of fabric, what you're doing is adding dye molecules to the fabric. So you start off with, let's say, a white piece of fabric. The fabric is made of strands of chemicals, polymers, or there might be natural polymers. In the case of wool, for example, that's keratin, which is a protein. It's hair, effectively, from the sheep. And so this is lots of amino acids linked together to make these long strings. And when you dye something, you're immersing that white substance or colourless substance in something which can impart a colour to it. So how does it do that? Well, chemicals are the colour they are because they reflect the light that is the colour that you see. So if you see a colour red, for instance, if I'm looking at, a jumper and it's a red colour, what that means is that the red jumper is soaking up all of the colours of light, apart from red light, which are being reflected from the surface, and those are the colours that you see. So how do we make a surface do that? Well, different molecules interact with light differently. So if you have a big molecule which has lots of electrons in the molecule, which can soak up light of a certain wavelength, then this means that the molecule will reflect light of different wavelengths. So you can, by changing the chemical signature of the molecules, what you're doing is making them so they're more likely to soak up light of certain wavelengths. And if you have a black substance, it's soaking up light of all wavelengths. So you come up with a series of chemical molecules that will lock on to the fabric particles, the fabric molecules, and tightly bind onto them so that the two effectively become one. and then the material is dyed that colour. And you can sometimes make that happen by adding some kind of fixer. So adding some acid or some alkali, for example, can activate the chemical that's the dye and make it more sticky, so it makes it chemically more likely to bind onto the fabric that you're dyeing. And then once it's on there, it will continue to soak up energy from light and reflect light of a different wavelength, so you get the colour that you want. Now, light contains quite a lot of energy, and especially if you have something in strong sunlight for a while, the energy in the light, when it hits that substance, can not only be soaked up by some of the molecules, but sometimes it can also break them down. So you give energy to certain parts of the molecule, and this can make the molecule break up. So over time, the dye molecule itself, instead of just soaking up the energy and redistributing it, gets broken apart. So effectively it chemically changes, and if you lose that chemical configuration that soaks up that light of a certain wavelength, giving a surface its colour, then it appears to fade, and it gets lighter, because a lighter surface is one which is reflecting more light. And this is a good party trick you can do on your friends. If you get a page with lots of colours printed all over it, and then a white piece of paper, and you ask your friend which surface has got the most colour on it, they'll inevitably say the one which has got all the colours painted on it. But the actual answer is the white one, because it's reflecting all of the wavelengths of light. In other words, all of the colours. So when a surface becomes faded, it's reflecting more white light because it's absorbing or soaking up fewer other wavelengths of light. So that's why you get fading with sunlight.
Leon is from Lowestoft, and he says that recently having 2 stents put in as an angina sufferer, he would like to know how much truth there is that hard water is bad for furring your arteries, therefore making his condition worse. What do you think, Dr. Chris?
I think it's an interesting question. First of all, what is angina? Well, angina is the pain you get in your chest when the blood vessels, the coronary arteries that supply your heart muscle, get blocked. Now, they can be blocked up in the same way that any blood vessel can be blocked up, and this is what we call heart disease. When you have high blood pressure or high cholesterol or don't eat a very healthy diet, or you just have a familial predisposition to this happening, what happens is that layers of fat called atheroma build up in the wall of the artery and they narrow it. And this means that the amount of blood that can go down the artery is reduced. And so when the workload of the heart, for instance, when you take exercise, run upstairs, go and dig the garden, when you put more load on your heart and it tries to increase its oxygen demand by increasing the blood flow down the coronary arteries, it can't, because there's an obstruction upstream. And the heart responds to this by generating a pain, which we call angina, and it's fairly central in the chest, and it radiates out down your arm, often into the neck. It can go through to people's backs, and it usually goes away as soon as you stop doing the thing which is making it happen. And this is the giveaway symptoms that doctors look for, that the patient might be suffering from angina. And ways to treat it are to either reduce your exercise or how much load you're putting on your heart. You can also take drugs, including something called GTN, which is glycerol trinitrate. It's very similar chemically, actually, to TNT, so it's pretty explosive. And if you put this under the tongue, it gets absorbed into the blood supply, and it causes blood vessels to relax or open up. And this can take the workload off of your heart, and also helps to boost the flow of blood down the coronary arteries a little bit. And the combination of those two things make the symptoms go away. But that's only symptomatic relief. So how do we treat the problem permanently? Well, the answer is that you need to unblock the artery. Now, in the early days, what doctors were advocating was a coronary bypass. And what this would involve is to go into the chest, and you either borrow a piece of vein, usually one from the leg, which has got lots of muscle in it, called the saphenous vein, or you can also use an artery that's running down the inside of the rib cage, the internal mammary artery, and you use this either vein or this artery to connect to the coronary arteries downstream of the blockage. So what you're doing is providing another route for blood to get into the coronary arteries and therefore supply the heart muscle. This is not trivial surgery. And whilst it's extremely good at saving people's lives and improving people's lives, it's dangerous in the sense that you've got to go into someone's chest. And this means that there's a risk of infection and all the other risks of hospital stays and anaesthetics and things. It's also quite costly, and the recovery times are quite long. So in recent years, there's been an approach which is called endovascular repair, or PCI, percutaneous interventions. And what this means is that you open up a hole in an artery in the leg, the femoral artery, and you thread a catheter up inside the artery back to the heart. And where the main artery of the body, the aorta, meets the heart, just after it meets the heart, on the arterial side, are two branches that come off called the coronary arteries, and you can get your catheter into those. And what doctors do is to squirt dye down into the coronary arteries, and they can then watch, using an X-ray camera, the flow of dye down the coronary artery, and this enables them to see, A, where their catheter is, and B, where there are any obstructions. And then what they do is to position the catheter directly adjacent to these fatty build-ups in the wall of the artery, and you then inflate a balloon inside the artery, just for a short time, which squashes the obstruction, stretching open the artery and allowing blood to flow freely. Now, that was the first thing they used to do, and it used to give immediate relief to people, and they felt much better. The problem is that when you do that, it damages the wall of the artery a little bit, and it causes it to try to produce growth factors, which encourage all of the cells around the site that you've just done this to proliferate, because they think that they've been injured and they need to heal things up. And this proliferation would then end up making the artery narrow again, and sometimes it would get even narrower than before you'd done it. And so several months later, people had all their symptoms back. And then scientists and doctors discovered that a really good way to prevent this from happening was to use something called a stent. And this is where you have a tiny metal cage, which is initially rolled up, and you can thread it inside the artery. You inflate your balloon to open up the artery. Then you deploy this little metal cage, which is of a number of lengths, but usually a centimetre or so long by the width of the artery. And then you inflate the balloon inside that metal cage, opening up the metal cage like a ratchet. So it opens up and props open like a scaffold the artery. And this stops the artery closing up on itself again. And more recently, people have been trialling stents that are made of a material that's impregnated with a drug which can stop blood clotting, and it can also stop cells from dividing. And this is called drug-eluting stents. And the idea of those is that then you preserve the integrity of the vessel so it doesn't flare up again. This is a very, very good technique because patients only have it done under local anaesthetic. It's very, very quick. You can go home the same day if all things go well, and you don't have to have general anaesthetics, and there's much lower risk of infection. So it's very, very quick to do. It's low cost, and therefore it's very, very good for patients and for doctors. So it's revolutionised treatment of heart disease. Whether or not you can affect your rate of heart disease depending upon the water you drink, I don't know. I don't think there's any strong evidence linking drinking hard water with the formation of artery disease. If there is, it's probably nothing compared with the major risk factors for artery disease, which are smoking, diabetes, having high blood pressure, a poor diet, and a family history. And included in that means being male, because men are much more at risk of this at a younger age than women are, because women tend to be relatively protected until they get to their menopause. To my knowledge, hard water is not a risk factor, but high blood pressure definitely is.
Right, Leon from Lowestoft. Make sure you look after yourself then. Chris, thank you very much. We go to the phones. We have Alan from Orpington with a question about fossils. Hello, Alan.
Hello, Dr. Chris.
Hello, Alan.
I'm forever seeing fossilised dinosaurs and creatures from way back being discovered. And I understood that fossilisation was actually minerals that replaced the bones. The question is, when you see these, it seems as if sometimes the actual structure inside the bone is also mimicked by the minerals. What I'm wondering is, why doesn't it just go into a solid lump? The other thing is, you get a skull and the eye sockets are all exposed. And so is it possible that somewhere in there the deterioration of the bones matches the speed of pouring, say, plaster of Paris into a mould? Does it work like that, or does it just sort of, everything just turns into a mineral all at the same time?
Yeah, interesting thought. The way in which it works with fossilisation is that something has to die, and it then deposits its bones somewhere, and then they get covered with layers of rock, which eventually turn the bones into rock. Put in a more complicated way, the best way to make fossils is when there's mud around, because you need those bones and tissues to be covered over quick before A, anything attacks them, eats them and disrupts them, and B, before they get degraded. So the best best fossils actually turn up from what would have once been a riverbank or something. So something dies, it ends up next to the river, a flood comes along, and lots of sediment or silt washes over the top and encases the bony material and whatever else is going to be fossilised, the body matter, underneath a layer of silt. Low oxygen conditions, very hard for microbes and other organisms to break the bones down too much. And then you get more and more and more silt on top, and the pressure plays a part here. But basically what goes on is that the chemicals that are in the bones, and they tend to be the thing that fossilises best because they have the best structural integrity, the most strength. So the chemicals which are in the environment leach into the bones, and you get permineralisation. So you replace the chemicals in the bones with chemicals coming out of the local sediments. And this means that you then get effectively a rocky replica of the original tissue. People used to think, until not so long ago, that bones were literally, or fossils were literally just lumps of rock. But that's beginning to change, because there's a lady called Mary Schweitzer who I met in America a few years ago, and she made an amazing mistake in her laboratory. She was interested in trying to cut very thin sections through fossils from Tyrannosaurus rex leg bones, because she wanted to see what the level of detail was if you got right down with a microscope and looked at them under very high magnification. Now, one problem with looking at bones or fossils under the microscope is that it's quite hard to shine enough light through the surface. So you want to be able to see the surface in detail by illuminating it brightly. So let's get rid of a lot of the minerals and make it easier for the light to penetrate. That's what she was doing. She put some sections in a tank to demineralise in a solution called EDTA, and then went home for the evening and forgot about it. And when she came in the next day, she thought, oh, and said a rude word, and I suspect, and realised she'd left these things in EDTA for far too long, and she expected they would have just totally dissolved. But she thought, well, let's have a look anyway. And she was gobsmacked when she saw what looked like Tyrannosaurus rex bone tissue, protein, the stuff that was in the original bones, still in there. And closer inspection revealed what looked like tiny blood vessels, and in those tiny blood vessels looked like tiny blood cells. So she began to think, well, perhaps, actually, we've got minerals replacing a lot of the chemicals in the bone, but perhaps you can also store or save or preserve some of the original tissue too. And in the last few years, scientists have built on this discovery, and they have now proved that you are getting original dinosaur tissue back from fossils, and they have been able to take it to the steps where they, in the last few weeks actually, published some papers where they were showing that the sequence of the proteins, the amino acid building blocks that make up the protein collagen, which is one of the big building blocks of our skin and most of our body, for example, they were able to show how dinosaurs are related to birds today, because the collagen sequence in birds is almost identical to the sequence they were able to read from these 68 million year old Tyrannosaurus rex fossils. So the bottom line here is that a fossil isn't just a lump of rock, because there's likely to be some of the original tissue still in there. Some of the chemicals that were part of that animal's body are still likely to be there, although there will have been permineralisation, replacement of a lot of the chemicals with other minerals, and therefore a rockiness. And to answer your question about skulls with the eye sockets exposed, if you look at, say, some of the skeletons they've got in South Africa from the early humans, so 3 million year old specimens, a lot of the time they'll turn up in, Raymond Dart discovered the Tong Child, which is a very famous baby's face skeleton. And he had to chip away with one of his wife's knitting needles all of the sedimentary mud and rock, soft rock that had built up around the bone, but he could do that. So basically, where you've got an interface between the skull and the mud, you can chip that away, and that's how you get back to what would have been bone once before it got fossilised.
Is there any chance of DNA in any of this protein?
Well, DNA is, because of the sequence being so important and it's quite easy to contaminate, it's much harder to say there's DNA in here. People are looking for it. I don't think that they've been able to prove that there's any there. Proteins are more robust and they're more easy to compare and to work with than DNA. There is, however, work going on showing DNA from mammoths that have been frozen in the ice for about 30,000 years. There's also something called the Neanderthal Genome Project, which is just like the Human Genome Project that the Wellcome Trust and Sanger Institute down at Hinxton, not far from Cambridge, sequenced a third of. Now they're doing the same thing for our near relatives, the Neanderthals, who died out about 25,000 years ago. And so far, they have sequenced over 1 million genetic letters from Neanderthals and also proved two things. One, that there was a fair number of ginger people who are Neanderthals, so they had ginger people. And secondly, they proved that probably they just died out. They didn't mix in with our population. And the way they proved that is they cloned a gene they found a gene which was in their Neanderthal DNA, which coded for ginger hair, and they looked at the sequence of that ginger hair gene, and then they compared it with modern human DNA sequences, and they couldn't find any overlap between this gene sequence and modern humans with ginger hair genes. And so it looks like, rather than just being absorbed into modern humans, Neanderthals actually perished and went extinct.
That's it for this week. Our doctors will be back with me next week for more Ask the Naked Scientist. But don't forget, you can also catch them on the Naked Scientist podcast, which you can find on the Naked Scientist website, www.nakedscientist.com.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.